Yeah, why there's so many words? Oh, math. Okay, so here we go. The quantity R, all right, so this is a number, in grams of a certain radioactive substance decreases according to the exponential decay model. Oh, hey, they give us the model. Love it. D capital R dt equals negative 0.05 capital R, where T is measured in seconds. That's helpful to know, but this is multiple choice, doesn't really matter. During an experiment, a scientist determines that the rate of decay of the second substance with quantity, there's another substance, there's another quantity in grams as well, just like the other one, in grams, can be represented by a linear model. Oh, this is a linear model. That's right. This is the rate of a linear function, so that just means slope is -4. Where t is also measured in seconds. Actually, I want to write this in a different color. So d capital S over dt equals -4. Looks like they give us initial values. We're given when R is 100 at the beginning, which is 0. And we're also given when S is 125 when we're at 0. At what time in seconds will there be equal quantities of both substances? Okay, so if you know the formulas, you know the general families of each of these rates, you can just go straight to that. Like, we know this one right here because the rate is proportional to the amount. This is going to be an exponential function with base e. We know this one's linear. The problem even told us it was linear. But I can also do all the separating of variables and all that stuff to get my answer. So if you don't want to see me actually separate the variables, you can go ahead and skip ahead and get straight to the formulas. All right, I'm going to move this guy up, and then I'm going to separate those variables. Okay, here we go. So I would get D capital R. I'll have 1 over R in front equals, this would be 0.05 negative dt. And I'm going to integrate this side. I get natural log of R, absolute value, plus C sub 1 on the left side. On the right side, I get negative 0.05 times T plus C sub 2. I'm going to change this to a C sub 3 because I want to move that C sub 1 over. I'm going to raise both sides to the base E. And so I get R equals, and on the other side, because our exponents are adding right there, I can change this to be negative e to the negative 0.05 t times e raised to this constant c sub 3. This becomes a constant because it's e raised to a constant. It just gets you another number. It's almost like saying e to the second power. It's just another number. But we don't know exactly what that constant is. But we do know it's going to give us another number. So we have C sub 4 e to the negative 0.05 t. Now we also know, so I'm going to say R written as t. We also know that this right here is the initial value. Now, which is 100 right here. And if you want to find out for yourself, plug in 0, 100 into the T and the R to see what C is. You'll see that it's 100. Okay, so I'm going to put 100 right here. All right, that one's done. All right, we have our amount function for the first radioactive substance. For the other one, let's see, we're going to go move this dt over here. Then we're going to integrate both sides. Bam, bam. On the left side, we get just S. Plus a constant. On the right side, we get 4t plus a constant. And I'm going to combine these constants to get C sub 3. And now I have S equals 4 of t plus C sub 3. Again, for this one, though, our initial value is 125. Okay, so if I plug the 0 in right here, and I put 125 in right here, then you would clearly see that S of t would equal 4 of t plus, and our C sub 3 is 125. Okay, so we have our two functions right here and right here. Now, it says, at what time in seconds will there be equal quantities of both substances? Okay. the only way to do this, well, you could try to solve it. You just set them equal to each other and solve it. Or what we can do is use a graphing calculator. And this one actually is a calculator problem. On the College Board exam, you click on that guy and it'll take you straight to Desmos. So let me show you guys what Desmos looks like. Let's see. Where's my Desmos? There's my Desmos. Okay, so I'm going to throw those guys in here. We have 100, and then we have times E. So there's my E raised to, shoot, I can't remember what it was. It was raised to the negative 0.0 t. Negative, okay, raised to. Now, I think you have to use parentheses to stay in the exponent. Negative 0.05. I think I said 2 earlier. And I'm going to use an x instead of a t because I know this. I think you can use a t, but I'm going to use x because that's the normal one. And then we can't see it. Can't see our function here. But if I zoom out a little bit, we should be able to see it. There he is. And then for the other one, I believe it was, I can't remember, 4t plus 125. Okay, so we got 4 times x plus 125. And wherever it, there's a problem here. Is it a negative 4? Do I have a negative 125? Yeah. Let's see. I messed up. Oh, I couldn't see the negative right there. Stupid. Okay. So it's supposed to be a negative 4. So let's put a negative in front. There it is. Okay. I know the t on the other point where they're intersecting. That one, the negative 10, that one doesn't matter because it's negative seconds. So our answer is, the t is 23.548. Let's look at our choices. 23.548. There you go. All right. Now I'm going to show you guys what it looks like with a graphing calculator, because you can do this with a graphing calculator too. So first go to y equals. Okay, so it's 100 and then E. So it's second ln. There's your E. And then it's negative. Make sure you use the negative button right next to the decimal. Negative 0.05 times x. And there's my x button. And then I'm going to go down to put in my other one. It was negative 4x plus 125. Now, if I hit graph, my graph doesn't look bad. All right, it went from negative 10 to 10. If your window looks weird, just make sure you hit zoom and then 6, and it'll standardize your window. But I can't see either function, so I'm going to zoom out. Let's go zoom out. Actually, instead of zoom out, let's do zoom fit. All right, if you scroll down, you see where it says 0. That's zoom fit. That'll put the function kind of in the middle. But it looks like it's cutting off my other point of point of intersection. That's right. And so I'm going to go back to zoom 6. And I'm going to say zoom out. So zoom 3. There it is. There's that point of intersection. So I'm going to hit second and then trace at the very top. And there you will find a bunch of different operators that you can do on the graph. In this case, we want intersect. And so it's going to ask you 3 questions. It's going to say, wait a second. Intersect 5. That's right. Oh, okay. My calculator is saying left bound. Normally it asks what function do you want? Like you pick the first function, then you pick the second function. But I think what this calculator is doing is saying, okay, where's the left bound, where's the right bound? So I hit enter, and then the right bound, I'm going to go over here, enter, and it gives me x equals, you know what? Intersection. This calculator is wrong. It's doing this different thing. So if you guys have a Texas Instrument, it won't say, I think it's thinking that I'm looking for the zeros. Let me see if I can go down and select it. No, oh, there it is. See if it'll let me do it. Nope. Okay, my graphing calculator is not working right. But talk to me in class, and I can show you on your graphing calculator how you can use your graphing calculator to find the points of intersection.